Okay, so let's go on to tomography. Let's see. So we can actually, I'm going to change the order in which I go through the slides a little bit. Can we flip over to the slide? To the paper? Oh, there we go. So that's a CT scanner. They used to be called, and in fact, a lot of physicians still call them CAT scanners. So I think CT stands for computed tomography, and CAT, I think, was, I guess, sometimes the acronyms is a little uncertain what they stand for, but I think it's computer-assisted or tomography. So they took the A out, and now they usually refer to it just as CT. That's the more sophisticated term, really, CT. So CT scanners look like this, and it's an example of a 3D imaging modality. Another 3D imaging modality is MRI that we'll also talk about. People often confuse MRI and CT because, from the point of view of the patient, it's just another big white tube that you get into, and it makes a picture of you. Okay, but they're completely different. Okay, I mean, superficially they seem the same, but once you get into the issues of what they're really doing, they're totally different. Okay, not only is the physics of what's going on very different, but the mathematics of what's going on is very different. Okay, and we'll see that. As a matter of fact, they represent two very distinct different techniques. There are many modalities that use tomography to reconstruct images, not just CT. CT is a specific one. I think I'll mention in here, I don't know if I will, okay, but there's another thing called PET, or positron emission tomography, and PET uses also tomographic reconstruction as well as CT, but the imaging modality is quite different because the physics behind it is very different. And there's all kinds of applications in which people do tomographic reconstruction, and more generally we'll see that tomographic reconstruction is really an example of an inversion process where you basically have a linear transform and you're trying to invert the linear transform. Okay, so tomography CT is a special case of a broad and class of methodologies that have application in medical imaging, also non-destructive testing or sensing. As I know that we have people in the audience here in the class who are interested in applications like radar, SAR. It can also be viewed as a problem in tomography sometimes. So it's sort of a special case of a broad class of problems of what I would say would be growing importance. So and then MR is not a form of tomography. Magnetic resonance imaging, MRI or MR, is not the same. It's distinctly different, has a different kind of set of equations, and we'll talk about that. So we'll learn about the two, sort of canonical examples, you might say. Okay, now in CT, like I said, it's kind of a white donut. The patient lies down on the bed, and the bed, you hear a whirring noise, and then the bed translates through here, and then the technician calls on a little phone, and they go, Mr. Bouman, you can get off now. Okay, and then you get off, you go home, and then they call you up later, and the radiologist is a physician, so they're an MD, medical doctor, or they're licensed to practice medicine, and they actually read the scan. Usually the radiologist doesn't actually physically take the scan, but they read the scan, they look at it, and they make a diagnosis from it. So, and the scan is a three-dimensional object. So the difference between CT and MR and older imaging modalities like X-ray, the classical planar X-ray, is that this is three-dimensional. And see, it's three-dimensional, and classical X-ray imaging is two-dimensional. Okay, so that's hugely different. You might say, well, this is a 3D image. This is a 2D image, but this is a 2D slice of a 3D reconstruction. You have voxels in 3 dimensions. In planar X-ray, you just you put the you have like the person lying down on a bed, and then you have an X-ray source and you have film underneath there, and you have the superposition of everything. So when you look at the image, you see backbone superimposed over heart, superimposed over liver. Okay, so because of that, it's much more difficult to make a diagnosis from what sometimes they call this a chest X-ray. It's a planar X-ray. Okay, and when you have a source of light, of X-rays, and you have, in the old days, of course, you had photographic film. Now you may have a digital focal plane array, basically, that can capture digitally and measure the number of X-ray photons, and you form a 2D image by the and if you basically you take the log of this thing, and they usually reverse it so that the points with very few photon counts are displayed as white, okay, and the parts with very little a lot of photons counts are displayed as black, okay. So that way, soft tissue looks dark, and bones look light. Okay, that would be a classic X-ray that you'd be used to seeing. You could display it any way you want, but that's the way people are used to looking at it, and that's the way radiologists are used to looking at it. Okay, but this is 2D. Okay, this is 3D. Okay, so how does that work? How do you form a 3D image of a person without actually slicing them up? Okay, which most people will object to. So how do you do that? Okay, so well, that's where the magic of tomography comes into play. So in tomography, what happens is that, this is kind of a strange-looking person, but imagine that this is what a person looks like, okay? So they're like this. And here the person is uniform density, but it could be that they don't have uniform density. It could be like that's their backbone, okay? And what will happen is that the idea is that in tomography, tomo means slice. So this is Greek, I think, for slice. So in tomography, what you're trying to do is take slices through something and use that to reconstruct what the thing looks like, okay? So here, in the planar X-ray, at every point, you try to measure the line integral of the density through the material. Now, what's density? What's line? What does this mean? I'm going to be more specific in a moment, but I'm giving you the general idea. So if you get the projection through the object at each point, so at every angle, theta, you get the 1D image of projections. Mm-hmm. And then if you have that at every angle, then you can reconstruct the image. So it's as if, like, if I'm in a room. Okay, could we come on show me personally? Like, take the camera onto my, yeah, right there. So if I'm looking at something and I have an object here, okay. So and I'm looking at something with the object, and I can't see around it because the object blocks my view. Okay, so if I tilt my head, I look at different angles, I can see what's behind the object, right? So that's the intuition behind tomography. That by looking at different angles, you can get different views, and you can try to find a consistent interpretation of all the views. If you only have a single view, there's information you've lost. But if you have lots of different views, you can put them all together to have a single 3D interpretation of what's going on. It seems like a massively complicated problem, and it's not obvious how to go about doing it, and that's where the mathematics is going to come into play. So let's go back to the slide. Okay, so here, so we're going to have this projection, but we're not going to just have this projection at one angle. We're going to have it at all angles, okay, and then we're going to have to reassemble it. So how do we reassemble it? Well, there's going to be a thing called, so by the way, f of xy, that's the thing we want to reassemble. F of xy is a function of x and y, okay? And then the projection of that is going to be p sub theta of r. So P is a projection at a particular angle theta. We're going to get a function of r. So we're going to the actual tomographic instrument makes measurements of P of theta r from f of xy, and then the question is, so this is the physical world. This is our CT scanner, and then from this we want to go back and get that. So this has to be mathematics. Okay, so in this direction is the CT scanner. This is the scan. And this is the math reconstruction. So this is computed. Okay, And this is called inversion because the physical system measures something, and then from those measurements you want to invert that to get back into the original quantity. Okay? So how are we going to do about doing that? Well, there's a beautiful theorem called the Fourier-Slice theorem that tells us how to go about doing it. Now, the Fourier-Slice theorem is like the atomic sledgehammer of CT. Okay? But it doesn't exactly tell you, it gives you the beautiful theory to solve your problem, but it doesn't really quite go about telling you how to actually get the problem solved, okay? It doesn't exactly tell you what you should do on the computer. And there's lots of ways about using this theory to get the answer, but a lot of them are not very practical. So the practical way of actually getting the reconstruction is called convolution back projection. Well, there's actually lots of ways you can do it, but the conventional, most widely used method is called convolution back projection or filtered back projection. And that's actually the technique that we're going to use to actually do the reconstruction. Okay, so now, so I think I talked about this. Anatomical imaging modalities, chest x-ray, I talked about that. Computed tomography, I've talked about that. And magnetic resonance imaging, I've talked about that. We're going to talk about it in a lot more detail later, okay? Now, these are all anatomical imaging mechanisms because they actually show you what the human physical form looks like. I mean, they show you the physical location and position and shape of your bones and the soft tissue and so forth. But they don't necessarily tell you what that tissue is doing, okay? What's very interesting is what's called now functional imaging modalities. Functional imaging modalities take this a step further, and they actually look at what is going on biologically in the tissues that are being imaged. So SPECT is an example of a functional imaging modality. PET, which is also an fMRI, functional MRI. In addition, I mean, CT can do some functional imaging when you use contrast agents, but it's not its primary strength as a modality. It's not what people normally think of it as. Yeah.
So would an example of this be when you see in like hospital shows and you see like the brain lighting up different colors? Is that the kind of thing?
Yeah, that's functional.
Okay.
Right, absolutely. That's functional imaging. So an example of that in MRIs, you can actually do studies of what people are thinking. You can study how their motor cortex or higher level cognitive functions are behaving. Right, that's functional imaging. And then there's kind of the next thing that goes beyond that, and these are kind of fuzzy boundaries, honestly. Which is called molecular imaging. And molecular imaging, you're actually looking at the biological processes in cells, like gene expression and things like that. It's sort of a step beyond functional imaging.